Oh, yes, and hope everyone's okay here being recorded. Okay, so welcome. This is our breakout room. We're the Pfizer scope team for this year. To start with a project overview, Pfizer is has a patient-first philosophy, which drives them to create reliable and life-changing medication. And as a team of engineers, we wanted to create a system of wireless devices that monitored the environmental conditions inside of their supply chain. And the types of project impacts that this would lead to would be the automation of environmental monitoring of the barrels, so that could relieve manpower. Also, the reduction of waste in the supply chain, while also allowing Pfizer to create decisions supported by data on their particular supply chain, and even more importantly, to speed up the development process of life-changing medication.
So to give you some background of what our project is, let's talk about the items that we are actually interacting with. So that includes a drum. Now, a drum has a lid on top of it, and at Pfizer, these drums are used to store medical compounds. So that's what we see in the image on the center, where we have a gooseneck. Now, the medical compounds we have are contained inside of a plastic bag, and the plastic bag sits at the bottom of the barrel with the gooseneck sticking up top of it. The gooseneck and at the top of the drum barrel, we have a lid. And we have our entire device and system mounted on the lid so that it has a complete view of everything happening that's inside the drum. And on this device, we have certain components that we're going to talk about in the system architecture. So our system consists of multiple devices and multiple modules, which we are calling SensePs. A SenseP is a printed circuit board device that houses a bunch of sensors called the sensor suite, and it has a microcontroller on it. So the microcontroller is running code that takes in the data collected by the sensor suite and then process it in some fashion to perform calibration and send that data over to a network of devices that we are calling the mesh network. What is a mesh network? A mesh network is a collection of multiple SenseP devices. So since each drum contains one SenseP device, and a warehouse usually has multiple thousands of drums, all of these SenseP devices inside each of the drum together make up the mesh network. Now, at the end of the mesh network, we have another device called a queen bee. A queen bee is just is a controller SenseP with all of its sensors disabled. Queen bee takes all of the data coming from each of the SensePs through the mesh network and shunts it to a device we are calling our single board computer Raspberry Pi. The Raspberry Pi processes all of the data, and since it is connected to the internet, it takes all of the sensor data and stores it on a database that's called the MongoDB database. Now, MongoDB takes in live data in real time from our entire system, and then it's visualized on a different data visualization platform called Spotfire. We're going to now, so completely our system looks like, the next slide, please. So our full system looks like multiple thousands of SenseP devices connected together as a mesh network collecting data, and then that data being stored on a Pfizer database and being visualized in real time. We're going to go into more detail about each of these steps now.
So for our sensor suite, we have 3 sensors there. And the first sensor, the thermal hydrometer, it reports temperature and humidity readings inside of the drum. The next sensor is the headspace sensor, and the headspace sensor monitors the amount of inventory that's present inside the drum. How the headspace sensor works is it's an ultrasonic sensor, and so it kind of uses echolocation, similar way as a dolphin does, to detect distances of how far away it is from the particular device. And the particular device that we chose has multi-point detection, so they could see around the gooseneck that is present inside of most Pfizer's drums. And then the last sensor that one more. The last sensor that we picked was the accelerometer. And because our device is attached to the lid, we can detect if the drum has been opened or if it's been disturbed at all. And next slide. All of that data is being received by a microcontroller. The microcontroller that we chose is similar to ones that are used on a lot of Arduino units. And that controls our entire system. And that microcontroller takes that data and then sends it to the XP. And the XP, which is the chip that is responsible for connecting all of the boards together into a mesh network and is our communication between drums. And then now we'll talk more about the mesh network.
Yeah, so once we've collected data with those sensors, how do we get them to the analytics platform? So we do that with what we call a mesh network, which is a type of wireless network that we selected for its low power consumption and low cost characteristics. So in a mesh network, there's a few different types of devices. So first we have our sensor boards, which Uta was calling SenseBees earlier. Those devices basically sit inside the drum, and they are exclusively for sensing. That means that they have limited networking functionality, but that enables them to go to sleep and thus conserve power even further. After that, we have the router devices, which are shown in red. These devices can also also have their sensors enabled, but they have additional networking functionality. This allows them to all talk to one another and thus figure out the best route to get data from a given sensor to the network controller. To give you an example of what that looks like, consider this network where we have our network controller shown in blue, a few routing devices shown in red, and a few end devices or sensor devices shown in green. So if we had this network in a warehouse and we were to have some issue or need to remove one of those drums from the warehouse, say because it was being shipped to another location, some wireless networks would have a problem with this. They wouldn't be able to, we would just lose all data from those bottom two devices and have to redesign the network. However, in our mesh network, we're able to automatically reroute that data so that it always finds a path to the network controller. This gives our network a great deal of resilience to changes in the warehouse environment and makes it suitable for the Pfizer warehouse system. So once we've gotten that data to the network controller, we are then able to upload it to a secure instance of MongoDB on Pfizer servers. This allows us to basically continuously and in real time retrieve data about the state of the system in the warehouse, and instantly allows people within Pfizer's supply chain to visualize that data and analyze it for patterns. This will allow them to do things like dispatch workers within the environment, within the warehouse, to determine if there's an issue with a set of drums, or just reconsider policies within the warehouse.
Finally, we'd like to thank all of our awesome liaisons and advisors in scope. And at Pfizer, without you guys, this project would not have been possible. We really appreciate your support and we enjoyed working with you. Thanks a lot, everyone. This is the end of our presentation, and now we would like to take questions from everyone and talk more about the system.
Good job, team.
Thank you.
I wonder if you all could share. Oh, Katie, you're about to ask a question.
Sorry, I was looking for my unmute button. Nice job. This is really, really interesting and so cool. And I especially liked seeing a glimpse of the sonic measurement, so you could figure out what was actually in the bin. That's pretty cool. I wondered how and why you chose those 3 variables. I think it was on one of maybe the 3rd slide to track. Yeah. Oh, yes. Right. So the accelerometer, right? Headspace, and I'm not going to say that out loud.
Yeah. So no, go ahead.
Sorry. So we chose we chose the thermohydrometer, which measures temperature and humidity, because this was one of Pfizer's requirements. It's like the most important thing they're looking for is to make sure that the drugs are in the right temperature and humidity environment. Pfizer also requested that we look at the headspace, which is basically how much stock is present in any drum, because they would like to be aware of basically how that also affects temperature and humidity, and also how often like drums are getting depleted. Oh, sorry, yes, medical compound, I apologize. And we chose to add an accelerometer because opening the lids changes the environment within an individual drum. And so we believed it was important for Pfizer to understand how often they remove medical compounds from the drums affects the temperature and humidity within the environment.
Our previous solution for the lid opening consisted of a simple LED, but we realized that like the drums may be sometimes be in different conditions, so that a simple LED and the photodiode detection mechanism might not completely work. And that's why we switched to something that actually can track whether the lid itself is being moved in certain directions or not. And this actually provides greater depth of information about the devices being moved.
I'm wondering the extent of the implementation of this device. Did you guys implement it in a certain type of material that we have in the warehouse? Is the plan to implement it in all of the drums are already in the warehouse, or new drums coming in, and kind of what's the control measured? What's the plan that you left for Pfizer so they can continue the work that you're doing?
That's a great question. So at this point, if we can go to the system architecture slide. So at this point, we have a lot of our parts of our system working, and we have each of the SenseB devices detecting data, and we have calibrated our headspace as well as temperature and humidity data. So accelerometer is one of the parts that we still need to write some firmware for. And as far as the mesh network, the Queen Bee, Raspberry Pi, and data analytics go, that entire chain works like exclusively. So like we once we have data, we can display it in real time. I think one of the major parts that Pfizer needs to work on for this entire system would be to improve the security and the reliability of IoT devices, because IoT devices are generally known to be, let's say, insecure relative to other network protocols. So ensuring that all of the data that's being collected is in a secure environment and can be stored safely is something that needs to be done. And as far as the movement of the drums goes, this entire system is supposed to be mounted to devices and drums inside the particular warehouse. So usually, so far as we talked to Pfizer about it, all of these drums would be in a warehouse, and since they would be connected in a mesh network inside the warehouse, their movements within the warehouse could be tracked. But let's say if they were being shipped from one warehouse to another in a cargo vehicle, that vehicle would require an internet access in real time to actually monitor the conditions inside the vehicle and the drum inside the vehicle. I hope that clears it up.
Yes, thank you.
Do we have any more questions about the project or our experiences throughout the project? Oh, great question,
All right,
Noah.
great. Oh, go ahead.
Go ahead, Noah.
Okay, so what was a failure that you came across and learned from? We actually had quite a few challenges along the way. One of them was about partially through this semester, we switched the entire architecture of our system. Originally, we had a kind of mesh network architecture given to us by the old team. And we worked with it, and then we found that it wasn't exactly what we wanted to be doing, and we had more experience and ability to work with another network, or not network, device architecture. That device architecture that we switched to is an XV and Atmega system, which we switched away from a Silicon Labs EFR32 system. That was a very significant change, and I think we're better off for it. It required a lot of decision making and decision matrices and informed data collection decisions.
Another important, or I guess not exactly a failure, but a condition that we got stuck in due to the circumstances of the COVID pandemic was shipping and manufacturing. So usually lead times on devices for electronics are on the order of days and maybe weeks. One of the major problems we encountered at the beginning of this year and early February was that we had created an entire printed circuit board that's displayed on one of these slides. But that entire board was centered around one particular microcontroller, and that microcontroller went, I guess it's not here, but like that microcontroller went out of stock, and it had a lead time of around 49 weeks. And one of the reasons we chose to switch our system was that we could not find our entire main microcontroller that did all the processing on our printed circuit board, which was a challenge that none of us expected to have. And it's not usual, but due to the pandemic, there were a lot of issues in the semiconductor industry, and this was one of the very interesting challenges that we had to overcome.
Yeah. So I think that's going to end our Q&A session. Thank you so much for coming, everybody. Please make your way to the next breakout room session of your choosing. And thank you. And yes, we hope you have a good time at the rest of Scope Summit.
Have a great day, everyone.
Thank you.
Thank you.